Funding for this program is provided by Annenberg CPB to advance excellent teaching.
Let me start today by showing you a little demonstration that you've already seen before. I have here just a loop of wire connected to a galvanometer, which will tell us whether an electric current is running around in this loop. The laser beam, the spot on the screen, will move whenever an electric current runs in this loop. Now, all I have to do to make a current run through this wire is to take this ordinary bar magnet and move it into the loop, like that. Or out of the loop, or for that matter, move the loop into the magnet and back like that. And that makes a current flow, and that was really one of the great discoveries of the 19th century. Well, by now we have mastered all of the formidable machinery of electricity and magnetism. We know all about how to describe such things. So let's describe how that experiment works. What happens is that a current flows through the wire. That means the electric charges inside of the wire are set into motion, which means something applied a force to them. And we know what applies forces to electric charges. The force on the electric charge can either be equal to Q times an electric field if there's one present. That would make the charges move. Or it could be equal to the charge Q times the velocity of the charge crossed into the magnetic field. That would also make the charge move. Okay, that's our equation. Let's see how we use it to describe the experiment that we just saw. There are two possibilities. One of them is this. The loop is held stationary, not moving, and I take the magnet and I move the magnet into the loop. That causes the current to flow. Now, in that case, the charges in the loop were not themselves in motion. So it can't have been the magnetic field of the bar magnet that made them move. But since they did move, there therefore was an electric field. And so we conclude that a changing magnetic field moving the bar magnet created an electric field. And that, of course, was Faraday's great discovery of electromagnetic induction in the 19th century. And that's one explanation of that experiment. Now there's another, completely different, independent explanation. And that goes this way. Suppose instead I hold the bar magnet stationary and I move the loop. Now, of course, exactly the same thing happens. But in this case, we have no moving magnet, no changing magnetic field, but instead, the charges in the loop are moving because I'm moving the whole loop. They have the velocity v, and this velocity crossed into the magnetic field of the bar magnet gives us a force which causes the current to flow. And that also describes perfectly well the experiment that we just saw. So those two different phenomena, that is to say, this loop stationary and magnet moving, and this magnet stationary and loop moving, are actually two completely distinct, independent phenomena that have completely different explanations. When Albert Einstein saw that, he said, look, guys, you've just got to be kidding. Any yo-yo can see that those two are the same thing. So it was this simple little experiment that was really the starting point of the theory of relativity, not the Michelson-Morley experiment, not some exotic experiment to detect the motion of the Earth through the ether, but this simple little phenomenon that, of course, everybody knew about, but which disturbed nobody else except Albert Einstein. And what disturbed Einstein was not that we had difficulty explaining these phenomena. This equation explains them perfectly in every case. What disturbed Albert Einstein was the lack in the inner perfection of the theory. And what he did in response was to produce a theory, the special theory of relativity, which had just that kind of inner perfection. And it's that theory that we're in the midst of studying right now.
Historians recall the turn of this century as a revolution. No matter the field, from aviation to anthropology to art, departure from the norm was radical on all fronts. And the year 1905 stands as a crucial landmark. That's when Albert Einstein asked the world to get on the right track, to think for a moment about what a moment really is. Time is relative, he said, and a matter of simultaneous events. And in Einstein's relativity, which is reality no matter how it's looked at, simultaneity is a matter of opinion. Notice, for example, what happens when a light is switched on as Henry's train moves by. The light reaches the front and rear of the train at the same time. At least that's how Henry sees it. But consider an outsider's point of view. To Albert, at rest on the ground, the rear wall comes up to meet the light, and the front wall moves away from it. These two events don't look simultaneous at all, and that's the essence of the time problem. And in physics, the explanation of the problem starts with time dilation. Given the constancy of the speed of light, there's no doubt that a simple light clock, in motion, runs slow by a factor of gamma. But if a more conventional clock went along for the ride, would it slow down by the same amount? The answer is timely, because if only the light clock slows down, it might be possible to compare their times. Then if the times were the same, they would be at rest. But if the light clock were slower, that would be because they're in motion. But in motion with respect to what? The basic premise of relativity is that there can be no absolute motion and no absolute rest. And if those conditions don't exist, no experiment can possibly detect them. So if the theory of relativity is correct, every clock in the universe must behave exactly as a light clock does. And that's not just a discovery about clocks. That's a fact about the nature of time itself. Time dilation places the relationship between time and space in an entirely new light, which is exactly what was happening in art and literature in the early years of this century. In art as well as science, the idea of time and space was now far more than a passing fancy. Just as Einstein was trying to place everything in a new perspective, Virginia Woolf urged writers to move beyond the formal railway line of a sentence. And no writer innovated more with time and space than James Joyce. Like Einstein's world, writes critic Edmund Wilson, Joyce's world is always changing as it is perceived by different observers at different times. And so it went, around the clock, with scientists and artists, musicians and mathematicians, poets and philosophers. And Einstein's theory of relativity had gone at least as far as any creative imagination. On the track of relativity, velocity not only changes the nature of things, it changes the way things are perceived. That's because Einstein's relativity is a theory of motion as viewed by different observers. The theory applies everywhere, even Brooklyn, and includes all observers, even a good sport named Henry. They say Henry had one heck of a fastball. With it and a desire to pitch for the Brooklyn Dodgers, he was on his way to making the team. Some said Henry could fling a baseball at nearly the speed of light. And from his point of view, it does look pretty fast. But from where his pal Albert stands, it looks even faster. Could the speed of the ball, added to the speed of the train, make Henry's pitch look even faster than the speed of light? Of course not. Because even on a train in spring training, nothing travels faster than the speed of light. So what's really happening here? Baseball statisticians work it out using a space-time diagram, where from Henry's point of view, the ball speeds one way and Albert speeds the other way. And since distance is one axis and time is the other, speed, say v prime, can be seen in the slope of each path. Just as the speed of light is given by the slope of its path. On this graph, light goes 1 unit of distance for each unit of time. So, c equals 1. Meanwhile, Henry's pitch has a speed, u, sub x prime of 0.6, while Albert, going the other way, has a speed of minus 0.6. That's from Henry's point of view. On the other hand, as Albert sees things, the speed of light remains the same, but all other speeds are transformed because all slopes are measured on tilted axes. Of course, it's true that light still goes 1 unit of distance for each unit of time. So c is still equal to 1. But now, Henry's moving forward at a speed v equals 0.6. And the baseball's speed, u sub x, measures 0.88. In the strange arithmetic of relativity, no matter how you look at it, when one speed is added to another, the result is always less than the speed of light. So, while Albert will surely agree that Henry throws one heck of a fastball, he can always throw a little light on the matter. And be sure it'll get there first.
Even along the direction of relative motion, components of velocity never add to a speed greater than the speed of light. And the velocity transformation does affect components perpendicular to the motion, because although distances remain the same, time changes from one frame to the other.
Even when the theory's as beautiful as Einstein's, it needs testing. And there is a test of relativity in a phenomenon called the decay of cosmic ray mu mesons.
But we do have some clocks.
A quarter of a century ago, Dr. David Frisch of MIT and Dr. James Smith of the University of Illinois filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu mesons zoom straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2 millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour.
412? Oh, feet thick.
Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2 millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2 millionths of a second. A set of twins, born in virtually the same time and space, are on the surface very much alike. And yet, on the inside, may turn out as different as night and day. Being so different and so alike at the same time may be the ultimate paradox of identical twins. But in physics, the twins' paradox conjures up another image. And like Einstein's theory, it begins with an extraordinary fact about clocks. No matter how long they've been around, no matter whether they tick-tock, chime, or say cuckoo, all clocks obey the rules of relativity. Naturally, these rules apply to the human clock. With a time-keeping device called metabolism, it starts running even before the moment of birth. And in a relatively predictable fashion, it keeps running to the end. But what would happen if the human clock were moving at nearly the speed of light? To find out, consider these identical twins, Albert and Henry. From the very outset, their biological clocks start out in perfect synchronization. Soon enough, however, the best laid plans of mother and father alike get out of sync. Instead of an orthodontist, Albert becomes a scientist. Henry chooses what's left of the wide open spaces, open space itself. Especially for identical twins, the first parting is such sweet sorrow. Nonetheless, traveling at nearly the speed of light, Henry has no trouble leaving Albert behind. This is Henry's first long haul for his new boss, the Interstellar Baking Company. Destination, Zog, 10 light years away. Assignment, take a load of ordinary white bread and exchange it for Zoggy cakes, those delicious little buns that all the earthlings crave. But that's not what's so extraordinary. If Henry could compare his clock to Albert's clock, he would find Albert's clock running slow. And if Albert could compare his clock to Henry's, he would find Henry's clock running slow. And that spells paradox. How can each one be slower than the other? Fortunately, in the theory of relativity, there's no problem at all. For one thing, there won't really be a problem as long as the two of them are far apart. But what will happen when they're not far apart? Say, when they get back together for a family reunion. Again, in the theory of relativity, that's no problem. Brother Henry, at nearly the speed of light, will take about 10 years to reach Zog, 10 light years away. And then another decade to haul his buns back to Earth. To Albert, that's around 20 years. But to Henry, the twin who's actually en route, the situation seems different. Since it's Lorentz contracted, the distance to Zog seems like a milk run. A few hands of solitaire, 40 winks, and as far as Henry's concerned, it's hello to the bright lights of Zog City. Then, equally quick, because the distance is again Lorentz contracted, it's back to Earth just as fast. And so, when they do get to compare those biological clocks, while the result is amazing, there's no paradox at all. Henry, the twin who zoomed away and then came back, has only aged a couple of months. But Albert, the twin who never switched inertial frames, has aged 20 years. And so, even among relatives, time is relative.
Try to imagine, if you can, a completely empty universe, a universe with nothing whatsoever in it. In such a universe, it would make no sense at all to speak of time or space. The very concepts would be meaningless. If there were one single object in the universe, it would still be true. Time and space would have no meaning at all. If there were two objects, then you could imagine saying, well, they're getting closer together or they're getting further apart. And then you're saying something about the flow of time and distances. If there were many, many objects in your universe, you might imagine using some of them to construct a device that could measure the flow of time or measure the distance between objects. But it would still make no sense at all in that universe to say one of these objects is at rest and only everything else is in motion. In such a universe, the simplest law of motion it would be possible to imagine is to say that each body continues in whatever state of motion it has until something interferes with it. And that, of course, is precisely the law of inertia. But that has to keep on making sense in a universe in which light can propagate through the void. Now, if light has some definite speed as observed from a particular frame of reference, then there is such a thing as a state of rest in that frame of reference. And the whole argument for the law of inertia collapses. Now, I don't know if there are any other logically consistent universes. But in our universe, that problem has been solved by making the speed of light the same to all observers regardless of their state of motion. Knowing that, and only that, it's possible to deduce that if there are a pair of twins, and one of them stays behind on Earth, and the other one travels at high speed to a distant star, turns around and comes back, the traveling twin, when they get back together, will be younger than the one who stayed behind. I don't need to know anything about how clocks work, about quartz crystal oscillators, about human metabolism. All of those things are completely irrelevant. All I need to know is the principle of relativity and the constancy of the speed of light. And from that, I can deduce that the traveling twin will come back younger than the twin that was left behind. That is an absolutely breathtaking feat of pure human logic. That is the theory of relativity, and we'll get on with it next time.
Funding for this program is provided by Annenberg CPB to advance excellent teaching. For information about this and other Annenberg CPB programs, call 1-800-LEARNER and visit us at www.learner.org.